This is one of the most beautiful images in all of mathematics, and it is hiding inside one simple idea. An idea for solving equations that Isaac Newton had over 300 years ago. By the end of this video, you'll understand exactly how it works and where this picture comes from. Welcome to Mark's Scheme. Today, one of the most powerful tools in numerical methods, Newton-Raphson, the lightning-fast way to solve equations that have no neat answer. Here's a problem you can't just factor your way out of. X cubed minus 2 x minus 5 equals 0. There's no clean factorization and no formula in your toolkit hands you the answer, but graph it. And the answer is right there. The single point where the curve crosses 0. It's an ugly irrational number near 2.1. The question is, how do we hunt it down fast? Here's Newton's idea. Start with any rough guess. Call it x0. Say 3. It's not the root, but it's a start. Go straight up to the curve. Which straight line do we follow? The tangent. The line the curve looks like up close. Picture a nearby point sliding in. The line through the 2 points pivots. And in the limit, it becomes the tangent right at our guess. Now follow that tangent straight down until it hits the x-axis. The curve is hard, but a straight line crosses 0 in one easy step. That landing point is x1. And look how much closer it already sits to the true root. Now the magic. Just do it again. From x1, go up to the curve, ride the tangent down to the axis to get x2. Then again for x3. Each tangent slide snaps you dramatically closer to the root. After just 3 or 4 steps, the guess is sitting right on top of the root. Accurate to more decimal places than you'll ever need. That speed is why Newton-Raphson is everywhere in science and engineering. So why is it this fast? Here's the true root up top. What the matching digits as we step. After x1, one digit is locked. By x2, still settling, then it explodes. 3 correct digits, then 7. And here's the engine behind it. Each step, the new error is roughly the previous error squared. Square a small decimal, and you double its leading zeros. So you double the number of correct digits every single step. Mathematicians call this quadratic convergence, and almost nothing converges faster. Let's turn that picture into a formula. The tangent at xn has a known equation. Y minus f of xn equals the slope. Prime of xn times x minus xn. We want the spot where this line crosses the x-axis, so set y to 0. Rearranging for x gives x equals xn minus f of xn over f prime of xn. That landing point is our next guess, xn plus 1. There it is, the Newton-Raphson formula. Current guess minus the function divided by its derivative. Height over slope. Now the part most lessons skip. Because Newton-Raphson does not always behave. Pick the wrong starting point, and 2 things can go badly wrong. First, it can fall into a loop With this curve, a start at 0 sends you to 1. But from 1, the tangent sends you straight back to 0. Newton bounces between the 2 points forever and never finds the root. Second, if you start where the slope is nearly flat, near a peak or valley, the tangent is almost horizontal. Dividing by that tiny slope hurls the next guess far away, sometimes to infinity. The method falls apart. The lesson: Newton-Raphson is fast, but only with a sensible starting guess close to the root, where the slope is healthy. Choose well, and it's unbeatable. Let's do it for real, exam style. F of x equals x cubed minus 2, x minus 5. Start at x0 equals 3 and find the root to 4 decimal places. Set up the Newton-Raphson formula, then build a table. At x0 equals 3, f is 16, and f prime is 25, giving 2.36. Feed that back in for 2.127. Again for 2.095. One more step gives 2.09455. The first 4 decimals have stopped changing, so we can stop. The root to 4 decimal places is 2.0946. Here's a deeper question. Take a new equation with 3 roots. At -1, 0, and 1. Newton-Raphson finds a root, sure. But which one? That depends on where you start. Let's color every starting point by the root it ends up at. Mostly, it behaves. Start near a root, you fall into it. 3 clean bands. But look at the thin stripes, right where the slope goes flat. Near plus and -1 over root 3. In those slivers, nudging your guess by a hair, throws you all the way to a far-off root. Exactly the flat slope trap from before. Tiny cause, wild effect. And this is only the real line. Watch what happens when we open it up to the whole complex plane. Same idea, one upgrade. Let the numbers be complex, so every point on this plane is a possible starting guess. And use an equation with 3 roots: gold, green, and blue. Color every point by which root it falls into, just like the bar a moment ago. You'd expect 3 neat territories. Instead, the borders detonate into infinite, swirling detail. Newton's fractal, and it never stops. Zoom into any boundary, and the same intricate necklaces appear again. Zoom again, and again. Self-similar, forever. Infinite complexity, born from one tangent line. The same simple tangent step you just learned, hiding a whole universe. That's the quiet beauty of numerical methods. So that's Newton-Raphson. 1. Guess, then ride the tangent down to the x-axis. 2. The formula. Current guess minus f over f prime. 3. It's blisteringly fast because the error squares each step, doubling your correct digits. 4. Start near the root and watch out for flat slopes. It's a cornerstone of numerical methods, from your exam to real engineering. Next time, we'll meet the steadier methods, bisection and regula falsi, for when Newton refuses to cooperate. For Moyer, that's markscheme.app. See you there.